The first thing to know when choosing your cutter is what type of cutter it is. There are three main different types and they differ in the way that they remove cut material from the cutting tool. When you are cutting material, you generally want to make sure that your cutter is spinning at a speed that creates chips rather than dust, as this will provide a better surface finish. When the cutting face interacts with the material, it needs to move the chip out of its path so that it can continue unimpeded. The way that the cutter is profiled will define how the chips are removed. Traditional router bits are known as straight cut bits, as their cutting faces are aligned perpendicular to the cutting axis. They are basic in design and relatively low cost compared to some of the other designs on the market. Straight cut bits are useful for cutting through solid material which is not fully enclosed, so that the chips and dust fall away from the cutting tools, as there is no route to encourage them away from the cutting face. An upcut bit would be similar in design to that of a twist drill that most craftspeople are familiar with when they bore holes. The upcut bit is profiled so that as the cutting tool rotates, the chips are pulled up and away from the surface of the material. They are the most common bits found and are intended for solid materials and hardwood, more so than composites and plywood boards. Upcut bits tend to rip through the material when cutting through and can leave a jagged, unseamly edge on the visible face. However, because they can remove the chips efficiently from the cutting edge, they tend to be able to move through material faster and at a much higher RPM, meaning that a job can be completed much quicker. Downcut bits are, as the name suggests, designed to work in the opposite way to an upcut bit. Rather than pulling the chips up and out of the path of the cutter, they push them down and can lead to the chips being cut multiple times. For this reason, you must program the CNC to rotate slower and progress through the material at a reduced rate. Downcut bits are, however, the favoured choice for cutting through thin material, such as thin plastic sheets and wood veneers. They are also good at preserving the top face of the material, so if you're working on a piece that requires a clean cut on the upward face, then this is the type of cutter to use. Compression bits utilise both upcut and downcut profiles in their flute design to provide a combination tool that can be used at a higher speed through thicker material, such as the upcut bit, but without the potential damage to the top face, such as found on the downcut bit. They're particularly useful when cutting through plywood materials, which are particularly susceptible to splintering on either the top or bottom face when cutting through the full thickness of the material. To gain full benefit from the two different profiles, the compression bit must engage enough of the tool to utilise both the upcut and downcut of the profile. Cutting tools are made up of several sections that allow them to be used correctly. To properly plan and program your CNC, you will need to understand the different sections of the cutting tool and how they relate to programming the machine. The first way cutters are identified is through the profile of their cutting faces. There are many different types of cutter shapes and specialised cutters that can be bought or made to provide a specific profile to the machining. For now, we're just going to focus on the basic and most common profile shapes. End mills are flat-bottomed cutters and provide a profile that allows for a smooth and even finish on faces perpendicular to the cutting axis. They are often used for machining profiles as well as for cutting pockets in the material, which will have a flat bottom. When machining in 3 dimensions, an end mill is often used to quickly remove lots of material roughly before a cutter of a different shape is used to finish the part. A variation of the end mill, the bottom cleaning cutter, is very similar to that of an end mill, but is often used for planing faces as its large diameter relative to its standard end mill allows for the surface to be cut cleaner with fewer tool marks. Bits with a rounded end are often referred to as bull-nosed, bullhead, or cove cutters, and are cutting bits with a fully radiused end. These mills are used for providing internal radii between the flat and perpendicular edges inside a pocket and can be used for finishing where there are not lots of ridges and troughs. End mills with only a small radius rather than a full one are known as bull-nosed end mills and can act as an intermediary between a flat end mill and a bull-nosed cutter, and are useful if you want to create an internal radius without changing to a second tool. There are various types of tapered bit that can be used when machining and are useful for doing different jobs. Standard 45-degree bits are useful for machining a smooth and even chamfer to an edge, or are useful for engraving text and details to achieve a traditional carved look to a workpiece. Fully tapered mills are also available for machining fine detail in a piece of material. Cutting tools are simple objects but have several features that need to be understood to use them appropriately. When understanding and categorizing your cutters, you will need to know 2 bits of information other than the cutter profile, which we described earlier. The first is the diameter of the cutting face. This dimension is important for understanding how much material is to be removed in a single pass and whether a tool is a correct diameter to machine a feature, especially internal features like pockets. The more surface area of the tool that is in contact with the material, the slower a tool can progress through a material. However, there is also a sweet spot as the smaller the diameter, the more susceptible the tool is to being damaged. The next dimension that tools are often categorized by is the diameter of their shaft or shank. This is the part of the tool which is held by the tool holder. Sometimes a tool has a shaft diameter that matches the width of the tool, but often the shaft will be of a different dimension. Again, as with the diameter of the cutting face, the larger the shank diameter, the stronger the tool, and as such, you are likely able to be more aggressive with your cutting speed and depth. Some smaller diameter shafts can cut at higher speeds, but you may find that they are noisier than the large diameter tool. Understanding the overall length of your tool allows you to program how the tool can work in the Z dimension. Often, the overall length is not a critical dimension, but it is important to know how much of the shaft needs to be held within the collet of the tool holder. Often, a more important dimension is the length of the tool below the holder, as this sets the maximum depth a tool can move in the Z dimension, before the end of the tool holder meets the top of the workpiece, or any clamps or work holdings that you may have. This is also important when the tool is moving around the piece, as the machine may need to accommodate for this in its X and Y travel. If you have a shoulder on your tool, the machine will need to know the length below the shoulder to the end of the tool, so that it will know when it can move within a slot or pocket before the shaft encounters the material. After this, the length of the flutes is important, as this is the length that sets the maximum permissible cutting depth for the tool. You don't want to plunge the tool past this length, as you will end up with material that is not being cut correctly, and this could damage your machine.